Okay, so we're looking at section 15.1 in Rogowski. It's on integration in several variables. So what do we want? So we'll do it in the plane in two variables, x and y. So we really want to basically the way that we're going to write it is going to write two integral signs, meaning we're taking the integral of a two-dimensional thing. R is some. Let's right now suppose that it's a rectangle, right? This is the rectangle R, and we're trying to compute what this is, and the d is not going to be dx dy or whatever. It's going to be, we're going to write dA. Sometimes people write dx dy over here, and we'll see why that comes up. But it's really the area measure. So what is this? This is, you really want to think of it as let's draw. If we had the R was over here, and we had graph of a function, right? That's over this region R, right? Then the integral should be, if I drew that correctly, would be the volume under the graph, right? So it's really the height f times the area of the base, right? But of course, on each little, infinitesimal piece, we'll get to that in a moment. So it should be the volume under the graph, right? So for example, we can immediately say what if what if we have R has some width and height. So what is maybe let me call it W and then H for for short, so I don't have to rewrite it. What if we take some constant integrated with respect to dA? Well, that's when this is just a flat plane, so we get this sort of box, right? Where the base is width times height. That's the area of the base, and well, maybe I should call it depth rather than height of the, if the rectangle is sitting sitting on the side, it's a height when we're thinking of the plane as being vertical. So this is C. This side of the box times width times height, right? So it's just the C times area of R, right? Okay, well that's simple enough. What if we want to integrate a more complicated function? Well, the way it works is we take this R and we cut it into small pieces, and conveniently it's already sort of pre-cut, right? And in each one of these little pieces we're gonna pick a point, right? Let me draw a typical one of these little pieces, right? You pick a point. We're gonna call it Pij, because there's as I varies, maybe it's the which row it is, and which column it is, and maybe j is the which row it is. It doesn't really matter how you index things, but maybe it's the ijth ijth little box, right? That's what this is, and so I'm going to call this the Pij, right? And well, how is this box defined? Well, there's some. We're really cutting the x coordinates into pieces. So maybe, you know, the let's suppose it's the xi minus 1, xi, and y j, sorry, minus 1 and yj, right? And so then the size of this thing is what we'll call delta xi. This is going to be xi minus 1 minus xi, and similarly we have over here delta y j is yj minus 1 minus sorry, I'm writing it backwards. yj minus 1, and same thing here, right? It's this the size of this and the size of this. Okay, so now how do we how would we want to estimate this volume? Well, we're going to estimate the volume by taking the sum over all the i's and all the j's of f p I j, and then times the so-called the area element over here. Let's call it delta a I j, and this is just the width. So xi delta yj, right? So delta a I j, right? Now, this if this grid is fine enough, this estimates the area the volume under the graph fairly well. So we'll say if limit as is going to be a little vague, but if limit as the delta a I j, not really that, but let's suppose that as these go to 0, that's not quite exactly what it is, but as these little pieces get smaller and smaller, if this limit exists, call it this guy. And say f is integrable. Right? We can integrate f, right? So it's very similar, like in one variable, for one variable integral, or we're just doing it, in two directions. Okay. So that's basically sort of an overview of what the definition is, at least for two variables. And now, what do we have? The definition is not very useful for computing this, and it's not really it's fairly hard to show that some function really is that even exists, that we could try to estimate it or try to compute the integral, right? So there's a theorem: if f is continuous on a rectangle R, which and it should be it should really be given by closed intervals, then f is integrable on R. And what does this mean? Maybe if you're wondering what that means. It means that x is in this interval and y is in this interval, right? And these are closed intervals. This is a closed and bounded region, actually, as we discussed last time. Okay, so this says that if I have continuous functions, I can compute the integral, right? It doesn't actually tell us, how to compute it. It just tells us that we can. Well, that's useful. I mean, it is useful. If it didn't exist, there would be no point in trying to compute it, right? What you could do, and this is, a computer would do something similar. Not quite, but it could try to estimate it by doing those Riemann sums, the things that we defined over here. These are called Riemann sums, right? So you could try to do this, and you get the smaller grid you use, the closer to the actual value you get. And so you could do that. Computer can be really good in doing this precisely, and there are actually slightly better ways of doing this. And if you ask a computer to really give you an interval of something very complicated, it's probably the best that it can do. Now, if on the end, if you have a nice formula for f, sometimes it's possible to compute this a little bit more analytically, to get to actually use some calculus on this, right? And it's then it's probably better to do it that way. Now, one thing that helps with that is well, let's call it, since we're writing stuff as theorems, let's call it a theorem, is that the integral is linear. That means that if I have an integral over r of f back to a plus the integral over r of g back to dA, then this is the integral of f plus g, right? I just sum the functions. And similarly, if I multiply by a constant, so here c is a constant, and this is just the constant times the integral, right? All right, so that's useful. We can at least split up our work into sort of smaller pieces, right? If it's a sum of several pieces, we can integrate each piece separately. Similarly, if it's a constant times a function, we can pull out the constant, right? Just like you did in calculus 1. Now, what really makes it possible to integrate, though, is the so-called Fubini theorem, right? And it says that as long as f is continuous, and let's just suppose that that's where we're at, then what you have is, and it's defined on this rectangle, it's continuous on this rectangle, then this double integral over r of f dA of this thing, that's actually equal to this so-called iterated integral, right? And we could iterate it the other way around as well. F. Now, what does that mean? That really means that you should really think of parentheses over here. The parentheses are not strictly necessary because there's no other way of interpreting it. But really what happens is that we basically inside here, we sort of forget about everything out here, and we say, wow, that guy, it's a function of x. We can just keep y constant, and we can just integrate with respect to x, and we'll get a function of y. This thing is a function of y, right? For each y, I get a different number. And then I can just integrate that with respect to y. And I could do the thing in reverse. I could first keep x constant and integrate with respect to y, and I get a function of x, and then I could integrate that, right? Well, maybe let's do a couple of examples. Let's do some really simple ones. So let's first do something. Let's integrate. Let's suppose that r is going to be, let's do 0 to 1 and 0 to 2, right? That's r, and let's integrate, I don't know, xy squared ta on this, right? Well, so what is that? Well, so I use Pubini, and we can expand with respect to any, either one of the two variables. So I could maybe put xy squared, maybe put the x inside, right? So x goes from 0 to 1, y goes from 0 to 2, so that's over here, right? So now, what is this? So over here, let's basically forget about the y integral, and let's just do the x integral, right? So let's do it let's not get fancy. Let's just do the antiderivative, right? It's x times y squared. Y squared is just a constant, right? So I'll have x squared y squared over 2, right? I anti-differentiate with respect to x. X going from 0 to 1, right? And still dy, right? And it's good to, if you're doing this, to sort of keep track of the variable here, right? I know which one I'm plugging in here, right? So what is that? So it's still from 0 to 2 dy. So, but what is inside? Well, inside it's the thing with where x we plug in 1, and then we subtract the thing with x where we plug in 0, right? So this is y squared over 2 dy, right? That's what this is. This is y squared over 2. Okay, now I integrate that, right? And I will get well, I get y cubed over 6, right? Y is 0 to 2, right? And again, that's I can just at y equals 0, 0, so I can just substitute 2 in there. So it's 2 cubed over 6, or there's a one. There's a factor of 2 in 6, so this is 2 squared over 3, or 4/3, right? Okay. Well, let's do it another way. Let's just do this is actually also equal to. I could have set up the integral in the other way, right? Let's just see what we get if we do it this way, right? Okay, so if we have this, so now we integrate in the y first, right? So we keep this integral fixed. We take an antiderivative in y, so x is just a constant now. Y cubed over 3. Now y is between 0 and 2, right? Dx, right? And so 0 to 1, and now we plug in 0 and 2 over here. So we'll have, again, when we plug in 0, we get 0. When we plug in 2, we get 2 cubed over 3. There's still an x, right? So I'm gonna keep that x in there, dx, right? And well, this is I can write it like this. You can sort of do a simpler thing than we did over here. This is just 1/2, right? If I have if the integral from 0 to 1 of the function x, right, it's the area of this triangle. It's 1/2, right? So we get 1/2 times 2 cubed over 3, that is 4/3, right? It doesn't really matter which way you do it, or at least not always. Sometimes it actually it does matter, as we'll see later, but let's not worry about it. But if you can do both ways, then both ways will give you the same answer, right? They are different. In this case, they're not that different, but in general, they can be quite different integration, and they might seem to have nothing to do with each other, except that they end up at the same place, right? And really, you should think of as these three things as sort of different mathematically. They just happen to give you the same number, right? There's three different formulas. Well, this one is hard to compute. We just take sort of the limit of the Riemann sum. That's hard. These guys are easier to compute, but they're definitely sort of different expressions. It's just that they happen to end up with the same answer in the end. Okay. All right. So I think that's good for that's good for today, and that should basically tell you how you can compute these guys if you have them, right? So